will be in a couple of weeks. So I thought we'd just run through that and give you some feedback about exam technique and what we expect of you during the exam. So the exam's worth 50% of this unit. It's worth studying for, yes. So this exam is online. It's on the web page. You'll find exactly this PDF file. So we have 3 hours and 10 minutes reading time. Okay. So there are 4 questions in that 3 hours. So you should spend a maximum of 3 hours divided by 4, which is 3/4 of an hour on each question. Okay, 45 minutes. So when you're there, make sure you stick to that time because the marks are in that weighting. So each question's worth 25%. So just a few other things. It's an open book. No, it's not. It's a closed book exam, sorry. So there's a no against that. So you're not allowed to bring any notes in. No calculator. You don't need a calculator. And no other items. So make sure you don't actually bring any notes in accidentally because we've had cases of students that, you know, they have notes in their pocket and they get then put up for disciplinary action because they accidentally brought out the notes. So just be careful about that. You don't want to be failed for this unit because you accidentally brought some notes in, which can happen, unfortunately. So each question is compulsory and each question is equally weighted. The other tip that I would give you is in the 10-minute reading time, you should read the whole exam paper and pick out the questions you think are the easiest. And do that question, the easiest question first. All right, build up your confidence. You don't have to do it in order of the questions on the paper. So if you pick an easy question, you can do it not only quicker, but it builds up your confidence in the exam. All right, so it turns out question 1 in this paper is very easy. So what you will be doing is writing your answers in the space provided in the exam. So if there's only 2 lines provided, don't write 10 pages, okay? You can write on the opposite side as working and indicate that your answer's there if you wish. But this tells you, okay, 3 marks, 2 lines, pretty simple answer. Okay, so what is the idle time? It's the time when no process is ready to run except for the idle task, which is the default task in the real-time operating system. Okay, so here is the typical answers. So the idle time is defined as the proportion of time when no other task can run. That's another way of saying that. So you know about the idle task in the operating system. It's the default task when nothing else is ready to run. So that means all other tasks are blocked in this real-time system. So what is the priority of the idle task? Can anyone tell me? Let's say, for example, there's 64 priority levels. What would you choose for the idle task? Yeah, what's it? Yeah, 63, good. Very good. Okay, so you pick the largest number because the lowest number is the highest priority in the system. All right, so the idle task should only run when no other task is ready, so that has to be the largest priority number or the lowest priority. So what happens in the idle task? Does anyone remember? Yes, it increments a counter. And there's also a user-defined hook function that you probably haven't noticed, but you can call another task if it wishes. So yeah, you do an increment on a 16 think it's 16-bit, or it could be 32 bits in your system because it's a 32-bit processor. So the purpose is to keep track of the time of idleness in the operating system. So just note that this question 1.1 is worth 3 marks. So there's 1 mark per each answer there, so they should be very quick, short answers. So in a real-time system, the utilisation is defined in terms of the idle time. And when you read that, you might go back and change your first answer because you didn't realise we're talking about a proportion of time. So that typically happens when you do these questions. So this is really basic. This question is just there to get you started. It's just ridiculously easy. So utilisation is 1 minus idle time. Okay, if it's not idle, it's being used. So suppose there are only periodic processes running and they're defined in terms of their period T and E for the execution. Okay, how would you then define the utilisation? Can anyone give me an equation for that? Oh, it's only worth 1 mark. It's got to be easy. Yep, good. All right, so that's pretty easy too. So describe how the utilisation is measured in the operating system. So we've just been through that. We run this idle counter. It increments whenever there's idle time. So the maximum value of that idle counter in a 1-second interval is, when nothing else runs, is a baseline for the idle counter. It's a reference that we can call idle count max. So if anything, if the idle counter runs for less than idle count max in 1 second, you know that something else is running and consuming the time that it would have otherwise counted up. So you can then work out the utilisation based on that. So it's 1 minus the idle count divided by the maximum multiplied by 100. Okay, so the proportion of time of idle count divided by idle count max is the proportion of time the idle, or the idle process runs, the idle time. Yep. So you can rewrite that as 100 minus idle counter divided by this denominator, which has been pre-normalised. That's usually how it's done relative to 100. So how often is the utilisation measurement updated in MicroCOS2? And would there be consequences of changing the update rate? It actually runs at 100 millisecond rate, the latest version that you're running. So this is out of date. Yeah. But I'd still give you full marks if you said once a second, because that's what you've been reading in the textbook, but the operating system's changed since then. So you're not going to get penalised for that. Okay, so let's assume it runs once a second. What would happen if we change the update rate? Well, you get an update more often. That's obviously true, but is there any other negative consequences? All right, so the operating system would be less efficient due to utilisation calculations happening more often. That's pretty simple. The other problem is if you decrease the update rate, if you made it 10 seconds, you may overflow your idle counter as well. So you need to allow the number of bits to allow that to run for the appropriate time. So what's happening here is really you're averaging this over a period of time. And as you noticed probably in the lab, the utilisation jumps up and down every 10th of a second actually in practice. So it's quite noisy. If you want to average that out and see a flatter value with a lower variance, you need to provide a longer time for averaging. Okay, so what errors occur in the measurement of the utilisation on micro CO2 and how could they be improved? So we looked at that in lectures, and it's all about the rounding of the calculation. So here it is. Okay, so when you do this division, you can do that more effectively by rounding to the nearest integer percent value. And that's done by adding 50 before you do the division, and you'll get 50% improvement in error. The other problem is when the utilisation is actually 100%, in other words, the idle task never runs, and the statistic task doesn't get a chance to run because they're the two lowest priority tasks, then the utilisation is reported as 0. Should be reported as 0. Sorry, it is reported as 0, but it should be reported as 100%, and it's reported as 0 because it never gets to run the update, which is a bit of a nuisance. So you could solve that problem, but you'd probably need a third task that's higher priority than everything else to monitor what's going on. But that detracts from the efficiency. So yeah, it's not a simple matter to fix that problem. Okay, so you're then asked to describe the rate monotonic scheduler in the context of the real-time operating system. Can anyone describe that quickly? What's important about RMS? Yes, it's a static priority scheduler. And it applies to what sort of tasks? Yes, that's true too, yes. And they assume to be periodic tasks. So there are the important points. So static priority, and as you said, the shortest period gets the highest priority. And the highest priority task always runs. Okay, that's what static priority means. Okay, so how well does this scheduler perform for periodic tasks as the utilisation increases? It's a pretty open-ended question. So what would you discuss there? What have we talked about in lectures? Yep. Yep, so if you have a large number of tasks, periodic tasks that are running, if you have less than 69% utilisation, what happens? Yeah, it can always be scheduled to meet the deadlines. Okay, so it's all about guaranteeing to meet deadlines. If the utilisation is less than m, lots of 2 to the 1 on m minus 1, then you can meet all those deadlines. But if the utilisation is above that, what happens? Well, it can be either way. Sometimes it can be schedulable, other times it may not. So what about earliest deadline first? How would you describe that? Which is what you did in the lab. Number 1, is it static priority? No, so that's what you'd talk about. So how do you then assign the priority? You base it on the deadline. The nearest deadline gets the highest priority. That's all you need to say. So how well does this scheduler perform compared to RMS? So if I give you a problem that RMS can solve, can EDF solve that or meet all the deadlines? In every case, is that true? Yes, you're right. So if overhead kills you, then you won't perform as well. Yeah, so that assumes the overhead is insignificant. So well done, pick that up. But you notice that in the lab. Okay, compare the execution times of the scheduler itself for EDF and RMS. And how do these change as we increase the number of tasks? Bit of a tricky one, this one. So how does it, let's start with RMS. How would you rate the RMS scheduler? In fact, when you think about it, the MicroCOS2 is actually implementing a static priority scheduler. I mean, you can change priorities, but if you don't, then it's pretty straightforward. And we spent quite a bit of time talking about this, and you end up with a fixed, constant schedule time for that. Determining which is the highest priority task that's ready to run, that's really what it's about. So EDF has to sort the deadlines at the end of each task, which can take n log n operations for n tasks using quicksort. Okay, you heard of quicksort? So you don't have to know that, you just have to say it's the time it takes to sort n particular things, in this case deadlines. RMS is generally a constant time scheduler, particularly in a good, well-written operating system. All right, so that was worth 3 marks. You don't have to write an essay at 3 marks. So what about question 2? Well, it's about arbitration logic. So again, this is a gentle beginning. What's the purpose of arbitration logic in a computer system? You want to answer that? Pressure. All right, so you've used CPUs. What about a more general context? Can you describe it in terms of things that aren't CPUs and aren't buses? Yeah, so you'd put it in terms of shared resources, single access resource, and multiple requesters. Could be CPUs, could be a DMA controller on a bus, for example. Okay, so yeah, you want to frame this as generally as you can in these answers. Hardware allocation of a resource to a single requester at any time. Okay, so you want only one allocation per request for all the requests at a time. So what are the inputs and outputs? Well, that's easy. You just got n request lines and n acknowledge lines. You assert a request by a 1 on the request line, and then you wait for your corresponding acknowledge. Right, so let's look at this question. What constraints are placed on the inputs to an arbitration circuit? So what are the inputs? Quick, someone? Yep, request lines. So what constraints do you put on the request lines? They can. Yes, that's right. You have to, once you lodge a request, you've got to stick with that request until you get an acknowledge, and then you can drop it. You can't drop it prematurely, because that actually stuffs up the arbiter. So yeah, that's a good answer. So you can raise a request at any time the corresponding acknowledge is 0, but you can only drop it when the acknowledge is 1. So that's interesting. Okay, so what do you think the next question is going to be? What are the constraints on the outputs? Right, so anyone want to answer that? So we're talking about the acknowledge lines now. Yep, so only one acknowledge can be 1 at any one time. Is that all we need to know? Does it matter which one's 1? So we might have 4 request lines, request 1 and 2 assert, and then we assert the acknowledge 4. Satisfies those conditions, doesn't it? So you need something more than that. Yes. So here goes. All right, so at most 1 acknowledge is asserted at any one time, number 1. Acknowledge K must be held until request K drops. In other words, request K was actually asserted in the first place, which is the next line. So you cannot allocate a resource to a requester who has not yet requested. Okay, that makes a lot of sense. So these are pretty basic things, but they're logical. They're specific to this problem that you need to understand. Okay, is it possible to design a two-input arbiter that can resolve asynchronous requests within a fixed bounded time? Explain your answer. So you got a yes or no. Who thinks yes? Who thinks no? So just talking about two requests here, pretty simple. And you've all designed one in the lab, okay? But it's not asynchronous, the one you designed in the lab. It was synchronous. It had a clock. So who reckons no? Who doesn't know? Is it yes and no? The answer is no. Why is it no? Yep, so a metastable state can arise if you have asynchronous requests. That word is important. And it can last an indefinite period, so that's definitely a no. So here we have a two-input asynchronous arbiter circuit, surprisingly. So the above is two-input arbiter, that's good. What are the inputs and what are the outputs? Pretty simple question. Hopefully you can do this pretty easily. So there are your inputs. You know these are NAND gates, they're inputs, so clearly that's an input. And the rest have to be outputs. Okay, so what we have I/J and J/I. They've even been labelled in the right manner. Yep. So if we assert this line here is a 1, then that forces this to be a 0. And that 0 turns on that transistor. This guy, if that's not asserted, if you have a 0 there, that's a 1 as well. So you get two 1s. So these are like inverters. And you get two 0s coming out. So when you assert a 1 on one of the inputs, the corresponding opposite diagonal output is asserted. So what happens if we assert two requests simultaneously here? We get a metastable state in this cross-coupled NAND gate. Cross-coupled NAND gates are latch. So that latch will enter a metastable state where A and B are approximately the same voltage. So here's a timing diagram of this situation. All right, so we expect you to understand some pretty basic logic here. So once we get A and B here in a metastable state, they're approximately the same voltage. It'll take an indefinite time for them to exit that state. And when they differ by more than the threshold voltage, the output will get asserted for the corresponding input that wins in this difference. So in this example, J won in the sense that B dropped and A went high, which meant J was asserted on the output. Now, we went through this in lectures. If you don't remember, then you can look up this circuit here where the threshold voltage on the PMOS transistor, that's the one with the bubble here, is when that's exceeded in a negative voltage direction, that transistor can turn on, which then asserts the corresponding output. So it's determined by the difference in the voltages A and B. So here we've got B coming in, and that's compared to A. So the gate to source source voltage here is determined by voltage B minus voltage A. Okay, so this circuit can resolve requests, but in an unbounded delay fashion. So that's interesting. So question 3. Okay, so this is about this particular key design element of an operating system. So this is about how you find the highest priority ready task to run in Micro C OS2. So describe how this constant time scheduling is achieved that doesn't depend on the number of ready tasks. Okay, so we've been through this in lectures recently. So you remember that this is done in two stages. We look at the X component, which is within a group, and we look at the groups. Okay, so what we're looking for is a 1 in the most right position of the group. So if that was here, then you'd know that these two groups, which correspond to these two rows, are all zeros, in fact. So you only get a 1 in this corresponding bit if the corresponding byte contains a 1. So you can look at the group first to determine which is the highest priority group, and that's done with this unmap function. So you'll see the details here. So Y is the component down the index of the bytes of this table, and that's done with this unmapped table function, which is just picking out the highest priority bit within an 8-bit byte. And you feed in the group value, which is what we just looked at, this thing up here, to find Y. Similarly with X, once you've found Y, you look within that component to find the highest priority bit, and that might be here if these two guys here were 0. And that gives you your highest priority in constant execution time. So that's all described here. So that works because you have a lookup table. This OS unmapped table is a lookup table that is accessible in constant time. Right, this question's quite interesting. And I suggest you do this yourselves later. We won't go through everything. I might just flip across to the other one and we'll look at it. So what we have here are different scenarios in an operating system with multiple tasks running. And you've got to apply the two tasks. One is mentioned in the question, and the other one is implied in the question as well. So the task under consideration is listed in this for each of these cases, and you've got to classify that task as ready to run. Excuse me. It was running, or it was in the wait state. So let's do an example. So if you call OS time delay from the current task. So what's the task under consideration? It's the current task. Okay, so you'll have a task and it calls OS time delay. So clearly that task is in what state that you're calling the OS time delay? It's running, yes. So you're obviously in this column here. All right, so once you are running, you can call this operating system function, OS time delay. What's the result of calling that function? So once you've called the function, what happens to the current task? Yeah, it becomes waiting. So you would write a 1 in this position here. Okay. So it's going from running to waiting. Okay. So what about number 2? We'll just do a couple of these. We're not going to get too excited. These are just testing your understanding of what actually happens in the operating system. So they're pretty easy, hopefully. So we call OS post called from another task, so that's not your current task that we're looking at. And the task under consideration is the highest priority task that's blocked on that semaphore with priority higher than the calling task, the guy that's calling OS post. Right, so what's going to happen? Anyone, one of you guys over here want to have a crack at this? Front row. Yes. Okay. Does everyone agree with that? Okay, so you've got another task posting on a semaphore that you, as the highest priority task, are blocked on. So what happens? You become unblocked, all right, and since you're the highest priority task, you will then run. Okay, so the task under consideration is going to end up running, and it's called from another task. So yeah, you go from waiting to running. Yeah. Okay. Is there any other one you want to look at before we move on? You can have a go at these in your own time. So once you finish this, you should have lots of numbers in this table. Okay. Just note, however, number 8, OSM penned on a semaphore with counter 0, called from the task with priority 1 above the task under consideration. All right, so what's going to happen is you're calling the OSM pen, so you're going to block. Right, so we know we're going to call from the task with priority 1 above the task. Okay, so the task under consideration is not the one calling this OSM pen. It's got priority 1 above that task. So what are the possibilities? So the guy that's actually running is going to be blocked. And this guy has a priority level 1 above you. So what do you think is going to happen? So you're going to go from okay. Yes, which is what? Could be, yeah. So you could go from ready to running. Okay, so if you happen to be lucky in that this guy is 1 above you in priority and it blocks, so then you become the highest priority task, so you run. So that's this number 8 here, from ready to run. Okay. Is there another possibility? Yes, there is. The other possibility is this guy penned on a semaphore. There could be another, okay, so while this has happened, there could be another task made ready to run that's even higher priority. It's unlikely. It'd have to be from an interrupt source, actually. So this case here, from waiting to waiting. So in other words, there could be a higher priority task that runs, but it's not very.
Just above the running before.
Yeah, I would say this guy is almost 0 probability.
That one might be if the task under consideration was already blocked. It's still blocked on something else.
Oh, okay, yeah, you're right, actually, yes. Yes, that's true. So you could have been blocked and then this makes no difference to you. That's what you're saying, yeah. Sorry, that's correct, yeah. Okay, yeah, it is a bit complex, that one, yeah. Okay, so let's move on. So with question 3.3, we've got 2 events that can occur, and they could be A and B. And we want the task should block until either A or a B occurs and then proceed. So we've got this task that blocks, waiting for an event from A or from B. You don't know which order they come in. How would you do this? You cannot do it with semaphores. Why not? So you might wait on semaphore A followed by wait on semaphore B. The problem is if B occurs before A, then you'll block on the first A and not get to B. Okay, so semaphores will not solve this problem. Now I'm being a bit mean to you guys because we didn't actually get round to looking at event flags, and that's what they're useful for. So that's what this is about. Okay, so to solve this problem you need to use a different primitive, and that's called the event flag. And that's what you see here. So the way that works is you'd set up this event flag group, it's called, and it contains two events. And then you can do this OS event pend on that event flag and you wait for any bit to be set amongst this bit mask, which is the OR of these two events. Okay, and that operating system primitive will return when you get an event on either of those two sources, which is rather nice because you don't then have to assume anything about the order of those events. So the event is signaled using OS flag post call. So this is sort of just letting you know about these event flags and how they would work. But I can tell you in your exam you will not have any questions on this event flag stuff. It's not fair because we didn't get to teach it. All right, but it's good to know about it anyway. All right, so question 3.4 was really about this sync function that we've talked about a lot in lectures. All right, you'll remember that we call this function from n different tasks, and the idea is to synchronize their activities so the fastest waits for the slowest in that situation. So here is the code that we got to in lectures, and we looked at this code and we discussed it. So this is not perfect, it has problems with it. So this is an initial attempt at a solution. Can anyone tell me what some of the problems are with this code? So what we're doing is we call sync, we count the number of arrivals when that's equal to n, the number we're waiting for. We reset that counter and then we post to all of the other guys that were waiting on this semaphore down here. Okay, remember that? Yes? So what were the problems with this code? Yep, very good. So you need a mutex to protect these variables in here. Yes, and what else? So num_arrive is a shared variable, needs a mutex protecting it from multiple access. We had a problem with the call, the nth call arrives, and in this example we've got 3 tasks. Is in 3 here, doesn't matter. So you then issue 2 posts for the other 2 block tasks. The first guy can come around very quickly and grab another pend operation. So you imagine this guy is posted twice and the first guy to receive it is released and then immediately calls sync again and grabs another copy. And that's the problem. The third guy never gets released then. So that's the difficulty. And you can solve that, as we discussed in lectures, by alternating between 2 semaphores, and then you end up with this code here. So I'm not going to spend time on this now, but you can have a look at that later. And you'll notice this local copy of this sequence. We discussed how that worked as well, because it can change once you leave this critical section at this point here, which then destroys the synchronization. Okay, so that's just a bit of analysis, if you like. Okay, so question 4 is about stack usage. So you remember the stack is used for local variables, save registers, interrupts, return addresses, and parameters. So tell me why you allocate a different stack for each different task in the operating system. Why would you do that? Why not have one stack and everyone uses the one stack? Yeah, it gets all jumbled up and you'd end up taking someone else's local variables on the stack and just getting in a hell of a mess. The return addresses all be wrong. So yeah, you have to, because the context switch can happen at any time, you need to keep them separate. Okay. So if you have a preemptive context switch, then you've got no idea when that's going to happen relative to your storage on the stack. If you have a cooperative kernel, you can probably get away with putting in the context switches at safe times, but that's still a bit tricky. So this question is about stack checking. How would you implement this, and how would you determine the size of the stack in a real application? So you use this stack checking function, and you need to understand how that works. So we discussed that just last week or last lecture. You just fill the stack with zeros and you count from the low memory to the first non-zero. That's the free stack space that's available, and you can keep track of that. And in practice, you should allow a little bit of headroom. Okay, so here is another question which is relevant. To fixed precision. So this is something you're doing in the lab at the moment, effectively. So you've got arithmetic operations, including addition, subtraction, and multiplication. 16 by 16 gives 32-bit in multiplication. And we can divide 32-bit by a 16-bit integer division to give a 16-bit quotient, and we throw away the remainder in C. And we can do shift left and right in our formulation of our solution. So what we'd like you to do here is to implement this expression here, a very simple expression using fixed point form, where we assume the result is required as an 8 integer 0.8 fractional representation. And we're going to assume here that the integers, the inputs A, B, and C are in 8.8 form as well. So how would you do that? So let's look at A multiplied by B. So you've got 8.8 multiplied by 8.8. So what's the result of that? Just quickly. Yeah, 16.16. So how would you convert that to 8.8? Yep. So you're writing a C program. You've done this for the PID controller. How would you do that? Yep. Anyone? Yeah, you'd shift to the right 8 bits, and then you'd chop off the left bits by allocating to a variable of limited size, typically. Okay, what about C divided by D? How would you formulate that? You want the result to be 8.8. If you did 8.8 divided by 8.8, you'd end up with something 0.0. Okay, you're throwing away all your fractional bits in the result if you do it that way. Okay, so what do we do for the division? So what do I put in here? We can do something to C to make sure the result gives us 8 fractional bits. Yep, anyone? We shift left C, how many bits? 8, right, got there in the end. Okay, so if you shift C left 8 bits, divide by D, then the result will be 8.8 if you store it into a 16-bit variable. All right, so is that the answer? So we do A times B, we shift that result right by 8 bits, and we add it to this. Are we finished? No, what do you want to do extra? Plus 128. Okay, where do you want to put that? In here, maybe. Okay, so you want to do rounding. Okay, that's good. All right, so here is the result, which is actually what you said. So we've got A times B, we add 1 shifted left 7 bits, which is 128, which is what you said. And that then gets shifted right 8 bits, so that provides rounding. Effectively, you're adding a half before you do the shift. And then we do the division, but we also put in D shifted left 1 bit to the right, I should say. So that's effectively D on 2 divided by D. So again, a half is factored in there. So this is actually the correct answer. All right, so don't forget about rounding in this sort of problem. All right, so the final question, I think we're up to it, yes. This is about the pendulum lab. It's describing the solution for interpreting a pendulum with a single sensor, beam sensor in this case, single light beam sensor, and you have to describe how you process this. So this is what you're doing tonight. So I won't show you the answer to this quite yet, but we've talked about the interrupt service routine has to record the time of the transitions in the light beam sensor. And I think we came to the conclusion you need to store at least 4 of these, or possibly 5, depending how you do it. All right, so have a think about that tonight. Who's actually done it? Yep, okay, 1, no? Yeah, completed. All right, so you've got, tonight you've got an extra hour. In fact, I think Sharia has agreed to hang around till 10 o'clock, but don't tell anyone else. So yeah, you can hopefully finish that tonight, and the report's due on Friday, okay? So you need to submit reports. Each person has to upload a report, even though they're written jointly between 2 of you, okay? Yeah. So you can write a joint report, you've worked with a partner, and you can upload the same report, the 2 of you. All right, so it's half the work, hopefully. Oh. Well, you're providing all your source code, so you don't have to replicate that in the report, obviously. You have to discuss the questions that are raised in the actual notes. There's various questions there, you might notice. You have to describe the performance of your system, honestly, and you've got to tell me how you'd fix any problems there are, because that's important. If you know how to fix something, you'll get credit for that. So there's a section at the end you'll notice on the Moodle site that how would I improve my final result? So if you had more time, what would you do? So yeah, you can outline that in half a page, whatever it takes. All right, so if you do have a problem and you know how to fix it, you're going to get credit for that. But if you have a problem and you don't know how to fix it, or you don't even acknowledge it, then you will get a lower mark. Actually, that's the way we do things. Because in industry, when you're working on a problem, your boss wants to know what resourcing is required to complete the task, typically. And do we need extra people to do this? What are the issues? How would we plan that work? So that's really what that's about. Right? We want you to be mature about your design. No design's ever finished in reality. You can always improve it, so we want to hear about that. Okay. All right, so yeah, hopefully you will have fun. And I won't reveal the answer. It's not that exciting. It's really about what you've done in terms of checking these transitions to try and establish the correspondence between the transitions and the physical position of the pendulum. Right? So that's the key problem with the light beam sensor. And once you've done that, you can easily extract the period and the speed of the motion of the pendulum. Okay, so we'll finish there and I will see you in the lab.